It looks impossible, right? A metal tube, defying gravity miles above the Earth, carrying hundreds of people and tons of cargo, soaring through the air at hundreds of miles per hour. For millennia, humanity could only dream of flight, looking up at birds with a mixture of envy and wonder. And even now, with millions of flights taking off every year, there's still something profoundly magical about it. But it's not magic, of course. It's a spectacular triumph of physics and engineering. You've probably heard simplified explanations, like the wings are shaped a certain way, or Bernoulli's principle. And while those are parts of the puzzle, they don't tell the whole story. The truth is far more elegant, more robust, and frankly, more surprising than the answers you usually get. Today, we're going to pull back the curtain on one of the greatest engineering feats in human history. We're going to dive deep into the fundamental principles that keep these colossal machines airborne, unraveling the surprising physics of flight. By the end of this video, you won't just know that planes fly. You'll understand how they actually stay up, debunking some common myths along the way, and gaining a profound appreciation for the invisible forces at play. Prepare to look at the sky and those impossibly graceful metal birds in an entirely new light. So, where do we begin our journey into the mechanics of flight? With the four fundamental forces that are constantly acting on an aircraft, whether it's sitting on the tarmac or cruising at 35,000 feet. Think of these as a cosmic tug-of-war, with each force pulling in a specific direction. For a plane to fly steadily, these forces must be balanced. First, there's weight. This is the force of gravity, pulling the plane straight down towards the center of the Earth. It's determined by the total mass of the aircraft, the airframe, engines, fuel, passengers, cargo, and it's an unrelenting adversary that the other forces must overcome. Opposing weight is lift. This is the upward force that directly counteracts weight, allowing the plane to leave the ground and stay airborne. Lift is primarily generated by the wings, and understanding how it works is the core of our discussion today. Then we have thrust. This is the forward-pushing force that propels the aircraft through the air. It's generated by the engines, whether they're propellers spinning to pull the plane forward or jet engines expelling hot gases to push it. Thrust is essential for overcoming the resistance of the air and achieving the speed necessary for flight. And finally, there's drag. This is the resistive force that opposes the plane's motion through the air. Imagine trying to run through water. That resistance you feel is drag. Air, though less dense than water, still creates significant drag on an aircraft. It's the constant friction and turbulence caused by the plane's shape and movement. So, in summary, weight pulls down, lift pushes up, thrust pulls or pushes forward, and drag pulls backward. For a plane to accelerate, thrust must be greater than drag. For it to climb, lift must be greater than weight. For steady, level flight, lift must equal weight, and thrust must equal drag. It's a delicate, dynamic balance, constantly managed by the pilot and the aircraft's sophisticated systems. Now, while all four forces are crucial, the one that often sparks the most curiosity and misunderstanding is lift. How exactly does a massive metal object generate enough upward force to overcome its immense weight? This is where the real physics comes into play, and it's far more nuanced than simple explanations often suggest. Let's start by addressing a common misconception, one that you'll often hear in simplified explanations: the idea that the curved top of the wing forces air to travel a longer distance, making it speed up to meet the air traveling under the flatter bottom at the trailing edge. This faster air creates lower pressure, Bernoulli's principle, and that's what creates lift. While Bernoulli's principle is absolutely involved, and the wing's shape is critical, this equal transit time explanation is, unfortunately, a myth. Air flowing over the top of a wing actually reaches the trailing edge sooner than the air flowing underneath, not at the same time. If it didn't, it would create a void, which physics abhors. So if that's not the full story, what is? The true secret to lift lies in two interconnected phenomena: Newton's third law of motion and Bernoulli's principle, working in concert to create a pressure differential. Let's begin with Newton's third law. For every action, there is an equal and opposite reaction. This is arguably the most fundamental way an airplane generates lift. Imagine sticking your hand out of a car window, tilting it slightly. What happens? Your hand gets pushed up. You've just demonstrated a fundamental principle of lift. By tilting your hand, you're deflecting air downwards. The air, in turn, pushes your hand upwards. This is the essence of what an airplane wing, or an airfoil, does. Even a perfectly flat plate, if tilted at an angle to the oncoming air, will generate lift. This angle is called the angle of attack. When the wing hits the air at an angle, it forces a massive amount of air downwards. This downward deflection of air is the action, and the upward push on the wing is the reaction, lift. The greater the angle of attack, within limits, and the faster the plane moves, the more air it deflects downwards per second, and thus, the more lift it generates. This is why planes pitch up their noses during takeoff. They're increasing their angle of attack to maximize lift at lower speeds. Now, let's bring in the wing's shape, the airfoil, and Bernoulli's principle. While angle of attack alone can generate lift, the carefully designed curved shape of an airplane wing dramatically enhances it, making it much more efficient. The curved upper surface and flatter bottom surface are not arbitrary. They are precisely engineered to manipulate airflow. When air flows over the curved upper surface of the wing, it accelerates. Why does it accelerate? Because the wing shape forces the airflow to curve, effectively pulling the air along the surface. This phenomenon is often aided by something called the Coanda effect, where a fluid stream tends to follow a curved surface rather than separating from it. As this air accelerates over the curved top, its pressure drops. This is Bernoulli's principle in action. Faster moving fluid equals lower pressure. Simultaneously, the air flowing beneath the wing is either relatively undisturbed or slightly compressed, especially at higher angles of attack, leading to higher pressure on the underside. So, what we end up with is a region of lower pressure above the wing and a region of relatively higher pressure below the wing. This pressure differential creates a powerful upward suction on the top surface and an upward push on the bottom surface. It's this net upward force, resulting from the pressure difference, that we call lift. Think of it like a giant vacuum cleaner sucking the wing upwards, while air pushes it from underneath. It's crucial to understand that lift is not just from the air pushing up from below, nor is it just from the air sucking from above. It's the combination of both the downward deflection of air, Newton's third law, and the pressure differential created by the airfoil's shape and the air's accelerated flow, Bernoulli's principle. One doesn't exclude the other. They are two sides of the same coin, describing the same physical phenomenon. The wing pushes air down, and the air pushes the wing up, primarily by creating a lower pressure zone above and a higher pressure zone below. The amount of lift generated isn't static. It's dynamic and depends on several key factors. 1. Airspeed. The faster the plane moves, the more air flows over and under the wings per second, generating more lift. This is why planes need to reach a certain speed on the runway before they can take off. 2. Wing area. The larger the surface area of the wings, the more air they can interact with, and thus, the more lift they can generate. This is why gliders have very long, slender wings. 3. Air density. Denser air, at lower altitudes or colder temperatures, contains more air molecules per cubic foot. More molecules mean more air to interact with, leading to more lift. Flying in thin, hot air at high altitudes is more challenging for lift generation. 4. Angle of attack. As we discussed, increasing the angle at which the wing meets the oncoming air increases lift, up to a point. Go too far, and the airflow can separate from the wing, leading to a stall, where lift dramatically decreases. 5. Wing shape. Airfoil design. The specific curvature and characteristics of the airfoil are optimized for different types of aircraft and flight regimes. A fighter jet's wing will look very different from a cargo plane's, as they are designed for different performance envelopes. So, when you see a massive jetliner effortlessly climbing into the sky, remember it's not magic, but the elegant interplay of its carefully sculpted wings slicing through the air, deflecting it downwards, and creating precise pressure differentials that literally pull and push the aircraft upwards. It's a testament to centuries of scientific inquiry and engineering ingenuity. While lift is the star of the show, it can't perform without a strong supporting cast, thrust, drag, and weight. We've touched on them briefly, but let's delve a bit deeper into their roles and how they interact with lift. First, thrust. Without thrust, a plane is just a very heavy glider. Thrust is the force that propels the aircraft forward, allowing it to achieve the necessary speed for the wings to generate lift. In modern aircraft, thrust is primarily generated by two types of engines: jet engines or propeller engines. Jet engines work on the principle of Newton's third law. They suck in a massive amount of air at the front, compress it, mix it with fuel, ignite it, and then expel a high-velocity stream of hot exhaust gases out the back. This powerful expulsion of gases is the action, and the reaction is the forward push or thrust on the aircraft. Think of it like letting go of an inflated balloon. The air rushing out pushes the balloon forward. Propeller engines, on the other hand, use rotating blades, which are essentially small, twisting wings. As these propellers spin, their airfoil shape generates lift in the forward direction, pulling the plane through the air. Just like a wing generates lift upwards, a propeller blade generates lift forwards. The main job of thrust is to overcome drag. Drag is the resistance an aircraft experiences as it moves through the air, and it's the constant enemy of efficiency. Imagine trying to swim through water. The water resists your movement. Air does the same, just to a lesser extent. Aircraft designers go to extreme lengths to minimize drag, which directly translates to better fuel economy and higher speeds. Drag comes in several forms. 1. Parasitic drag. This is drag caused by the non-lift producing parts of the aircraft. Form drag. This is caused by the shape of the object. A blunt, flat object creates more form drag than a sleek, aerodynamic one. Think of the difference between pushing a brick through the air versus a teardrop shape. Aircraft fuselages, landing gear, and external antennas all contribute to form drag. Skin friction drag. This is caused by the roughness of the aircraft's surface. Even seemingly smooth surfaces have microscopic imperfections that create friction with the air. That's why planes are often polished and painted with smooth, low-friction coatings. Interference drag. This occurs where different parts of the aircraft meet, like where the wing joins the fuselage. The airflow becomes turbulent and creates additional drag. Designers use fairings and smooth transitions to minimize this. 2. Induced drag. This is the most fascinating type of drag because it's a direct consequence of generating lift. Remember how wings deflect air downwards to create lift? This downward deflection doesn't just happen cleanly. At the wingtips, the higher pressure air from below the wing curls around and tries to equalize with the lower pressure air above the wing. This creates swirling vortices, like miniature tornadoes trailing behind the wingtips. These wingtip vortices create a backward component of force, which is induced drag. It's essentially the cost of doing business, the price of generating lift. Induced drag is greatest at high angles of attack and lower speeds, like during takeoff and landing, because that's when the pressure differential around the wingtips is most pronounced. This is why you see winglets on the ends of many modern aircraft wings. These vertical extensions help reduce the strength of these vortices, effectively recouping some lost energy and reducing induced drag, leading to better fuel efficiency. So, while thrust tirelessly pushes the plane forward, drag relentlessly pulls it back. For an aircraft to maintain a steady speed, thrust must equal drag. To accelerate, thrust must exceed drag. It's a constant battle, and the efficiency of the aircraft design is measured by how well it minimizes drag for a given amount of lift and thrust. Finally, we have weight. We already know it's the downward pull of gravity, but its management is critical for more than just overcoming it with lift. The distribution of weight within an aircraft is crucial for its stability and control. Engineers meticulously design where the engines, fuel, passengers, and cargo are placed to ensure the aircraft's center of gravity, CG, is always within a safe operating range. If the CG is too far forward or too far back, the plane can become unstable and difficult, if not impossible, to control. As fuel is burned during a flight, the aircraft's weight decreases and its CG can shift, which pilots and flight systems constantly monitor and adjust for. So, with these four forces in mind, lift battling weight and thrust battling drag, we can see the dynamic equilibrium that defines sustained flight. But how do pilots manipulate these forces to steer, climb, descend, and land? This brings us to the fascinating world of flight control. Pilots don't just point the plane where they want to go. They manipulate the forces of flight using a variety of control surfaces. These are movable parts on the wings and tail of the aircraft that subtly change the airflow and thus the lift and drag characteristics in specific areas, allowing for precise control. There are three primary axes of motion for an aircraft, each controlled by specific surfaces. 1. Pitch, nose up/down. This is controlled by the elevator, located on the horizontal stabilizer at the tail of the plane. When the pilot pulls back on the control stick, or yoke, the elevator deflects upwards. This pushes the tail down, causing the nose of the plane to pitch up. When the pilot pushes forward, the elevator deflects downwards, pushing the tail up and pitching the nose down. Pitch changes the angle of attack for the main wings, directly impacting lift and dictating whether the plane climbs or descends. 2. Roll, wing tilt. This is controlled by the ailerons, which are hinged surfaces located on the outer trailing edge of each wing. Ailerons always work in opposition. When one goes up, the other goes down. If the pilot wants to roll right, the right aileron goes up, decreasing lift on the right wing, and the left aileron goes down, increasing lift on the left wing. This creates an imbalance of lift, causing the plane to roll. Rolling is essential for turning, as a banked wing allows a component of lift to act horizontally, pulling the plane into the turn. 3. Yaw, nose left/right. This is controlled by the rudder, located on the vertical stabilizer at the tail. The rudder works by deflecting airflow sideways, pushing the tail in the opposite direction. If the pilot pushes the left rudder pedal, the rudder deflects left, pushing the tail right and causing the nose to yaw left. The rudder is primarily used to counteract adverse yaw during turns, a tendency for the nose to initially point away from the turn when rolling, and for minor adjustments to heading, especially during takeoff and landing. These control surfaces allow pilots to precisely orchestrate the interplay of lift, thrust, drag, and weight. For example, to climb, a pilot will increase thrust to overcome increased drag from higher angle of attack, and pull back on the stick, pitching the nose up. This increases the angle of attack on the main wings, generating more lift, and the plane ascends. To descend, they might reduce thrust and push the stick forward, decreasing lift. Beyond these basic controls, modern aircraft also employ other sophisticated devices to enhance flight performance, especially at critical phases like takeoff and landing. Flaps are hinged surfaces on the trailing edge of the wings, closer to the fuselage. When extended, they increase the wing's surface area and curvature, generating significantly more lift at lower speeds. They also increase drag, which is useful for slowing down during approach. Slats are similar, but they are deployed from the leading edge, front, of the wing. They create a slot that allows air to flow from the underside to the top surface, smoothing the airflow at high angles of attack and delaying a stall. Together, flaps and slats allow planes to take off and land at much slower speeds than their cruising speed, making runways feasible. Another fascinating aspect of flight is stability. Aircraft are designed not just to fly, but to fly stably. This means they have an inherent tendency to return to their original flight attitude after being disturbed by turbulence or a control input. Think of a dart. It's designed to fly straight. Its weight is forward, and its fins keep it stable. Planes achieve stability through various design features. Dihedral, the slight upward angle of the wings from the fuselage, V-shape, helps with roll stability. If one wing dips, the dihedral causes the lifted wing to generate more lift, naturally rolling the plane back to level. Sweepback, wings that angle backward from the fuselage, common on jetliners, also contribute to stability and allow for higher cruising speeds. Vertical and horizontal stabilizers. The tail section, with its vertical fin and horizontal surfaces, acts like the feathers on an arrow, providing directional stability and dampening oscillations. Modern aircraft, especially high-performance military jets, can sometimes be designed to be aerodynamically unstable for increased maneuverability. In these cases, sophisticated fly-by-wire computer systems constantly make thousands of small adjustments every second, effectively acting as a digital co-pilot to maintain control and stability, a task impossible for a human pilot alone. So, from the fundamental tug-of-war between four forces to the intricate dance of control surfaces, the story of how planes fly is one of profound scientific understanding and relentless engineering innovation. It's about harnessing the invisible currents of the air, not fighting them. It's about understanding pressure, momentum, and reaction, and then designing structures that can precisely manipulate these forces. To recap, aircraft defy gravity through the interplay of four fundamental forces: lift, weight, thrust, and drag. Lift, the upward force, is the star, generated primarily by the wings. It's a combined effect of the wing's angle of attack, which deflects air downwards, Newton's third law, and the airfoil shape, which creates a lower pressure zone above the wing and a higher pressure zone below, Bernoulli's principle, resulting in a powerful upward pressure differential. Thrust propels the plane forward, overcoming drag, which is the resistance of the air. Weight, the pull of gravity, is constantly balanced by lift, and pilots skillfully manipulate control surfaces, ailerons, elevator, and rudder, along with high-lift devices like flaps and slats, to fine-tune these forces and guide the aircraft through the sky. The next time you look up and see a plane soaring overhead, remember that it's not just a metal tube. It's a meticulously engineered marvel, a testament to humanity's endless curiosity and ingenuity, riding on the back of elegantly simple, yet incredibly powerful physical principles. It's a reminder that even the most seemingly impossible feats can be demystified and mastered through understanding the world around us. If you found this deep dive into the physics of flight as fascinating as we do, please hit that like button to help more curious minds discover this explanation. And if you want to continue exploring the surprising science behind everyday phenomena, make sure to subscribe to our channel and ring that notification bell so you don't miss our next video. What other impossible feats of engineering or nature would you like us to explain? Let us know in the comments below. Thanks for watching.